Welcome, everyone, to another evening with the Berlin Functional Programming Group. I am extra excited tonight because we have our first ever Rust talk, functional programming in Rust. I've been interested in Rust personally for quite a while. I haven't had a chance to really learn it properly. The most I've done is written merge sort. But I know it's the hipster language of choice right now, and the combination of Rust with functional programming was too good an opportunity to pass up when I saw Xavier mention something about Rust and formal verification on Twitter, when my mind was blown. And I had to invite him to the meetup. And fortunately, he was kind enough to accept my invitation and available. And so he is here tonight, Xavier Denis, who is a PhD candidate at the I'm going to give this a try. Laboratoire des Methodes Formelles.
Yeah, that's very good.
In Paris, where he studies the verification of Rust programs, which is not a thing I think anyone was doing. But apparently so. And in fact, he used to be an SRE at Shopify and somehow went from being an SRE to studying formal verification. That probably makes sense, actually, in some way. And I'm interested in hearing about how that transition worked out for you, Xavier. But this is going to be a really interesting talk. I think somewhat familiar and maybe a lot different given the kinds of talks we usually get. But I'm super keen to hear what you have to say. And I hope the audience is just as excited as I am and you ask lots of interesting questions, and we can have a chat. So I'm going to turn the spotlight over to you, Xavier, and thank you so much for joining us this evening.
Yeah, thank you so much for inviting me, and thank you to everybody who's come. And I hope that this will be interesting to everyone. And maybe someday in the future you'll be able to verify your Rust programs if you happen to be programming in Rust, or maybe this could push you to learn Rust. So as Stephen said, I'm a PhD candidate at the Laboratoire des Méthodes Formelles in Paris, and I'm studying the verification of programs, of Rust programs, but a little bit more generally even, sort of studying the verification of programs and languages with Rust-style typing. And we'll get into what that actually means during the presentation, and what we're doing with this. But in practice, yeah, I'm working on verifying Rust programs. As a little brief outline of what I'm hoping to talk about. So in the first part, I'm going to explain what deductive verification is, what we mean when we say we want to verify programs, and what we're trying to verify. We'll go a little bit over the challenges that happen when we try to verify programs that involve pointers, which is kind of like the core of why people use Rust, and also happens to be one of the reasons it's usually so hard to verify these kinds of programs. We'll then talk about the approach that I'm using in my tool and as part of my thesis. We'll talk about specifications of Rust programs, and then do a little bit of a case study / demo where we can look at verifying a program using pointers in a non-trivial way. So the very first question we can ask is, what do we actually mean when we say we want to verify a program? It's a phrase that you see talked about a lot on the internet, especially in sort of functional programming circles. You know, we always like to talk about how in Haskell we can use a type system to, help verify our programs or do some sort of formal reasoning about our programs. It's a phrase that's generally kind of overloaded. And it can mean a lot of things to people coming from different communities. You see some people who talk about using unit tests to verify programs, and in a way they are, because you're checking specific invocations of your program with specific function arguments. Then you get things like property-based testing, especially popular in Haskell, again, with the quick check library, which sort of generalize unit tests and help you check a whole class, potentially, of inputs and verify that they satisfy some property. So we're getting into this thing of basically there's a ton of different techniques that we can use to actually verify a program. But what we're really saying when what we're trying to say when we verify a program is that we want to check that a program satisfies some specification on, for example, its inputs and outputs, or it could even be something like its termination or non-termination. These kinds of properties. We're trying to check specific properties against a specific program, and so we have a whole arsenal of different tools that we can use to achieve different levels of confidence that our program satisfies those properties, and we can also use them to verify different kinds of specifications. Generally, the very first thing we want to verify when we talk about program verification is going to be something generally known as safety. And so this is basically just ensuring that your program is going to run. Safety basically means that we're kind of staying in the bounds of whatever our language is. So typically in most languages, if you do a division by 0, you get some sort of catastrophic error, for example. And so that would be typically an operation that would not be considered safe. In C and languages with pointers, we also get tons of other potential unsafe behaviors where, for example, we try to access to out of bounds memory or read from a dangling pointer, all these kinds of things. And so typically the first thing that we're going to do when we're trying to verify a program is that we want to check that it's safe. Again, when we're talking about unit tests, this basically just means, does your program crash when you run the unit test? But when we start talking about more formal techniques and formal reasoning, we want to sort of abstract this and check that, under all possible combinations of under all, every execution of your program, it's not going to crash, it's going to stay safe. But beyond safety, we start to get into functional properties of our programs. So these are going to be relations between the inputs and outputs of our program. This is what you may often have heard referred to as, for example, contract-based programming. This is also the kind of place where things like dependent types start doing things. This is really, proving things about your programs. It's saying like, I have a function that calculates the square root. Well, given some input, its output is going to be an approximation of the mathematical square root. These kinds of things. But there's a whole huge array of different things we may want to actually prove. And there's a whole bunch of different ways that we can express those properties. And sometimes we have to make actual choices. A common example, for example, is going to be things like temporal properties. If you've heard of tools like TLA, you can reason in what are called temporal logics, which allow you to talk about the sequencing of different operations in a sort of abstract time. Whereas then you're going to get tools like the one I've developed, Creusot, and many other tools which work more in a first order logic and don't really have a notion of time. But on the other hand, we may be able to express certain properties you would not be able to easily capture in something like TLA or a temporal logic. And then finally, you also have another pretty powerful property that we may want to prove on a program, which is going to be its termination or non-termination, actually. So of course, when we want to prove a program terminates, this is to avoid having infinite loops and having a program hang, which is going to be different from crashing. But we may also want to prove non-termination. For example, if your software is the flight controller of an airplane, you definitely do not want it to stop halfway through. And so these are two properties that you may also want to prove on your programs. And there are some more sort of complex edge cases and other things you may want to prove, but these are generally the most important and interesting things.
We already have one question.
Yeah.
Ulrich, would you like to? Ulrich, you're one of my favorites. Of course, you can unmute and ask your question.
Yeah, I'm just not so sure because I'm not so deep into all the formal stuff. What about the inverse, like proving that there are certain properties that you don't have in no, put it the other way around.
Yeah.
If I understand you, specification means you want to verify that your program satisfies a certain specification.
Exactly.
But what about stuff that is not specified, which your program might have in addition to that, like don't care inputs and it has some weird reaction and so on? Where does this show up? Does it just mean you have to specify more properly, or is that a separate category?
Yeah, it typically means that you have to specify more properly. So for example, if you want to say that your program doesn't care or won't do some behavior given a specific set of inputs, or doesn't care about the values of these inputs, you can actually write that as a sort of, I guess, positive, or a sort of positive specification saying, well, given in these cases, this is what my program will do. So you can usually transform whatever property you want into a sort of specification that you can verify. However, it may also be digging at another question, which is there's always the challenge of knowing whether or not you have the correct specification. And so you can also, prove things about your specification and verify your specifications themselves, proving, that they satisfy some sort of meta properties. This has been done in previous projects like Cell4, which is a verified microkernel, where not only did they prove that their whole thing satisfied a really complex and thorough specification all the way down to the assembly, but then they proved properties about their specification, showing that it had these like high level general properties that they were that they wanted to establish. Yeah.
Yep. Okay. Thanks.
Yeah. Did that answer your question?
Yep.
There's also another kind of, I guess, follow-up question from Bernd. You're already controversial, see? Bernd, do you want to unmute?
The inverse, that no additional properties are guaranteed, isn't that impossible to prove? Isn't it like it's like Gödel's and Turing's undecision and Entscheidungsproblem and the hiding problem?
Yeah, sorry, I guess I didn't understand. I should have looked at the text of Ulrich's question first. Yeah, proving that a program only has specific properties, I don't think that would be easily feasible. However, proving that it doesn't have a specific property is possible, because it's merely a question of showing that for all inputs some specific property does not hold. Yeah. But yeah, I don't believe that you would be able to show that a program that for all other properties outside of some listed property that they don't hold, apart from maybe trivial cases. Yeah. Sorry, I'm not. Yeah, sorry about that, Ulrich. I should have read the actual text of your question.
Yeah, but actually I should have maybe also made it more clear. Maybe I'm just having my mind sorted properly as well. Yeah. Because I always think about what then is the difference between having a specification. If the specification is 100% clear and it's declarative, then you're only left with the question if there is an implementation for that specification. If there is one, you should do it automatically, right? There should be no need to program anything. if there would be no creative step in between, why actually program? Why not just define a translate? Yeah.
I mean, that's the field of program synthesis, and there's a lot of very, very smart people working on that. It turns out that it's hard to write an accurate enough specification that we can synthesize a program. And even when you have a very precise specification, it's very challenging to find a program automatically that satisfies it. But they can do some really cool stuff too. Yeah. So if you've ever looked into formal verification, you may have seen a chart somewhere along these lines, which basically shows, there's this trade-off we get when we're talking about verifying properties of programs, where the more expressive the property we want to actually verify, or the more complex the property we want to verify, typically the less automation we get in Exchange. So at sort of the left-hand side, we have fully or nearly fully automatic verification of things through type systems, where at most we may have to write some type annotations here and there to help the type checker out in especially tricky cases. This can happen more often, for example, in Haskell, because the type system is incredibly rich. But pretty much all the time, we're going to be able to automatically know whether or not our program satisfies basic property, which is going to be something along the some form of safety property whereas like we're going to say that the arguments to your function are both ints, and therefore your function won't crash because all it's doing is an addition, these kinds of things. If we're willing to trade, then we get into automatic techniques like model checking. So maybe my placement of the model checking point is not entirely fair, but in model checking, we can prove significantly more expressive properties usually than we can with a type system. But usually in Exchange, it's not so much automation that we really lose, but it's that we're forced to use a significantly restricted language, or we're limited to a set of very small programs that we can actually check these properties for. So there's already some form of a trade-off here where we're gaining expressivity. We're starting to talk about potentially, things like temporal properties like we would in TLA. But we're going to be facing huge decision problems, and the algorithms, if they're decidable, are going to be X space. So they're going to be very, very hard to actually run on these computers. So there's a lot of efforts in making them tractable, but we get tons of challenges there. But still, these techniques it's still going to be a tool that you run on your code, more or less, and will tell you yes, no, maybe. And then as we move further along, we get things like deductive verification, which will be the subject of the rest of today, which are tools where you may have to start doing some manual proof work. You may have to place sort of assertions here and there and say like, hey, I believe this property is true at this point, and these kinds of things to help proofs along. But we're still throwing most of the work here at the computer. The computer is still going to do most of the nitty-gritty detail of verifying things. And then at the very far end, you get interactive theorem proving. So this is things like Cook or Isabelle or Lean, where we have incredibly powerful tools. We can use an incredibly powerful logic to reason about our programs, but we're sort of on our own for automation. So these tools typically have some form of basic automation, often in what's called a tactic language. But it's really nothing along the lines of any of the previous options. And if you want more advanced automation, it's usually up to you to build it on top of these primitives. So what we're going to be focusing on is deductive verification. And deductive verification is based off something known as Hoare logic. So Hoare logic is one of the oldest tools we have in the program verification toolbox. It was developed in the 60s, I believe, and has been refined throughout the years and applied to tons of different cases and in different languages and in different contexts. The basic element in Hoare logic is this notion of a triple. So a triple is going to be a combination of a precondition, some sort of command, and a postcondition. And basically, when we say a triple holds or is true, when essentially given a state where our precondition is true, after executing our command, our postcondition is going to be true. So it has this very intuitive explanation, especially when we think about imperative languages, where we're really executing things in sequence, right? We're really starting with some sort of preconditioning, evaluating things, and seeing seeing what we have after our evaluation. And so Hoare logic, the idea behind Hoare logic is that we associate a triple, one of these, a triple essentially to each syntax element of our language. So for assignment, we're going to define what the triples for assignment are going to look like, for arithmetic, for comparisons, for control flow, all these things. And then we can start reasoning about our programs by just recursively applying these rules that we have for our triples to the literal syntax of our program. And at the end, we can derive a proof using these triples, and we know that our program may satisfy some property. But the problem with this is that it still requires some amount of human insight. The rules we have for triples often leave some amount of choice in them, which is not very desirable when we want automated things. We want to be able to have sort of an automatic process for deciding which triples to use and what the P and Q are going to be at each step. And so here is a little bit of a small example and some sort of simple fragment of Rust, right? So it's just, what we're going to have here are assignments and arithmetic along with an assertion at the end. And between each instruction, I've annotated sort of the pre and post condition. So the idea is we start off with true, right, as our precondition to the entire program. We know nothing at the very beginning. But after evaluating our first instruction, which is just assigning x to be 1, well, we learn that, you know, x is going to be equal to 1. And then we evaluate our second instruction, assigning 5 to y. And again, we refine, our post condition grows here with additional knowledge. We know some more things, and we continue evaluating our program until we get, you know, z equals 6, which finally allows us to prove that z equals 6 here. And we can have any post condition, or we can have any trivial post condition here by weakening. So this process is quite powerful. It sort of corresponds intuitively to the way that we think about programs when we're looking at our own source code. We kind of, you know, step through the execution and say, like, okay, what are the different values of things at each point of our program? But as I said before, a big challenge is choosing the correct pre and post conditions. And so some very smart people back in the 20th century came up with this notion of the weakest precondition calculus, which is, just as the name implies, is a method to calculate the most general precondition for a specific command. And so the idea behind a weakest precondition calculus is that you take the post condition you have, you take your Q, and you take your command, and then you sort of run the command backwards to know, well, if I want Q to hold, what is the absolute minimum I need to know before executing my command? And so this is usually behind every sort of Hoare logic tool today, and many programs or many tools that are used to reason about programs. And it's going to be behind the tool. It's one of the key components of the tool I'm going to be presenting in just a second. And in some certain sense, it gives us the sort of best conditions to actually verify our program. If we want to prove that our program satisfies some final property Q, well, the weakest precondition is sort of telling us, here's the absolute minimum I need from you in order for Q to be true. The big problem, though, is that even with weakest preconditions, we often get huge formulas when we actually are looking at programs, because we have, you know, hundreds of instructions in a program. We have control flow, we have branches, we have loops, all these things. And so when we apply that weakest precondition calculus, we're actually building up this giant formula, this giant precondition, this giant formula that we need to check. And this would be incredibly tedious to actually solve by hand. And so the idea behind deductive verification is to combine this sort of weakest precondition calculus with SAT solvers, or in general automated solvers. So these tools have gotten incredibly powerful, especially in recent years, and you can basically just generate a giant weakest precondition and just throw it at these tools and see what they say. And they'll crunch through massive, massive formulas for you in split seconds. This technique has been applied to a bunch of languages. So the idea is sort of we generate the weakest precondition for a specific language, and then we throw it at a bunch of SAT solvers, and they tell us whether or not our programs are correct. Of course, there's a lot of details in between here that I'm alighting, but it has been used to verify C programs through tools like FramSC. It's been used as well to verify Java programs. I believe the tool for Java was called Krakatoa. There are several other Java verifiers. And it's also been applied fairly recently to verify OCaml programs through a tool known as Camelier. So one of the big challenges that we get, though, with these tools is verifying programs that have pointers. Pointers are going to be one of the most essential features in any systems programming language. They're a function that there's something that is underlying pretty much every abstraction we have in a computer. Even if your language doesn't actually have a native notion of pointers, it's pretty much going to have to be implemented in terms of pointers at some level. So even in Haskell, you know, when you write a data type, you're using pointers each time you make you have like a pair of types or something like that. But in the context of systems languages, we really start using those pointers to implement efficient and high performance abstractions. And they introduce a bunch of problems when we try to reason about them using weakest preconditions or using any tool, because they're incredibly powerful. And so the things that we need to check each time we use a pointer are incredibly tedious and challenging. And that is basically because the notion of pointer we use typically is that of C pointers. And C pointers are just too strong. They introduce a ton of problems. The first one is aliasing, which is you can have two mutable pointers to the same place in memory, which means that every time you modify one of those, or modify through one of those pointers, you're also changing the value you would read out of the other pointer, which means that somehow formally you need to have some notion that those two pointers are actually the same when you're verifying things. In C, of course, you get tons of memory safety issues also with pointers, and these are also going to have, you need to be able to reflect and reason about those in your formalism. This is going to appear in, for example, in your weakest preconditions as things like memory models. And we also use tools like separation logic to help control this explosion of complexity. But fundamentally, it's adding pointers to your language is a very serious decision that has very serious implications on verifying the correctness of your programs. And we can see this even with very trivial C programs. So for example, here we have pretty much the simplest program we could write. And so we want to ask ourselves the most basic question, is it safe? Which means, is it going to crash? Is it going to exhibit undefined behavior? Is it going to behave correctly with regards to the language? And here the answer is already no. Because we could have 2 pointers here that are both null pointers. We could have 2 pointers that point to invalid memory. We could have another issue which wouldn't actually cause a crash, but would make it fairly complex to reason about what's actually going on, which is we could have both parameters actually be the same pointer, or at least point to the same location in memory. We get this kind of issue all the time in C, which is going to require us to have a lot of specific reasoning about pointers, their behaviors, their interactions. And so the problems of memory safety, especially in C, is one of the motivating reasons behind Rust, which tries to leverages its type system to sidestep all these issues. And so the Rust type system is going to guarantee memory safety, and it's going to do that by restricting pointers, restricting the ways that we can use our pointers. And so this is what we know as borrow checking in Rust. These are mutable references and immutable references, lifetimes, these kinds of things. And so in Rust, the Rust type system has 2 specific features that it's going to use to implement these. This is going to be the notion of ownership and the concept of the notion of lifetimes. And so through these 2 things, we're going to be able to actually restrict ourselves to sort of a safe set of pointers that only exhibit simple behaviors, which we'll then use to actually make verification simpler. So in Rust, every cell of memory, every variable has a unique owner. That owner has exclusive read and write permissions. Whoever is the owner of some area of memory is the only one that's actually able to modify that memory. But we also have the ability to borrow those permissions for a specific lifetime. But when we make that borrow, when we take permissions to some area of memory, we have to make a choice. We can either have them mutably, but we have to have them exclusively, or we can have it shareably, but we lose the ability to actually modify memory. And all of this is going to be checked at compile time by the compiler, by the borrow checker in Rust's case. And it's going to be what gives us memory safety in Rust. And that's because I'm sorry, I should have gone back to this slide earlier, or stayed on this slide. It gives us memory safety. It gives us memory safety because having our lifetimes guarantee that every borrow is always going to point to something that is still alive. The idea is that when you create a borrow to some area of memory, you can only borrow it for a specific lifetime, and that lifetime must be shorter than whatever that memory, for whatever that area of memory's lifetime actually is. And so that's going to guarantee that we can never, for example, have pointers to uninitialized memory. We can never have use after free kind of things, kind of errors, because whenever we have a borrow to something, we know by construction that whatever it points to must still be valid. The aliasing, the mutability XOR sharing also ensures that whenever we have a mutable pointer to somewhere in memory, we know it's the only mutable pointer to that area of memory. And that's incredibly useful because it means that we don't have to worry about breaking or causing unexpected breakage in other areas of our code, because the only place that can ever read that memory is going to be whoever holds that mutable pointer, at the very least until we finally release it. And so if we were to rewrite that previous C example, we have pretty much the same syntax modulo the types, but we really have a very different behavior. Whereas in C, both of our pointers could be uninitialized or point to uninitialized memory or be aliasing. In Rust, we have none of those issues. By construction, we know that our mutable borrows are going to be pointing to valid U64s, so unsigned 64-bit integers. And we also know something additional, which is that they're pointing to different U64s. Since both A and B are mutable references, we know that they must be mutable references to different areas of memory, since we're only allowed to have a single mutable reference to each area of memory. And so we can ask ourselves if this program is safe, that is, if it's going to exhibit undefined behavior or crash, and the answer is no. I mean, except for arithmetic overflow. And that's because we have eliminated all those memory issues that were plaguing a C incrementation function. And so that's the idea behind Creusot, the tool I'm developing as part of my PhD thesis, is to leverage the Rust type system, not just to help simplify verification. We want as much as possible to lean on the information that Rust gives us through its type system to make verification significantly simpler than it would be in C. So Creusot is a deductive verifier for Rust built on a platform known as Y3. So as we saw, basically the idea of Creusot is going to be take Rust code and eventually generate a bunch of weakest preconditions for our Rust code, which we can then throw at a bunch of automated solvers. And they'll tell us yes or no whether a program is safe, which will mean basically that we're not going to crash unexpectedly or panic. But we can also use it to verify more complex functional properties. So we can actually ensure that our programs behave along in specific ways that we'd like to ensure. It's going to be limited only to handling safe Rust code. To verify unsafe code, our current plan is basically prove your unsafe code to be correct using different, more powerful tools. And then there may be some integration within Creusot to allow you to sort of say like, hey, this portion of the code has been proved in a different tool. Just assume that it behaves correctly or something like that. But for the moment, we're really only looking at at safe code. And we can handle, so we can also handle some forms of specifications for our code. So you're actually able to write specific properties that you would like your Rust code to satisfy. And have them checked automatically or semi-automatically. And it's available on GitHub for those who are interested there. It works. It's just very alpha software that, you know, it still can only handle, for example, we can't handle traits or things like that yet, at the very least. So as I said, the idea here is that we want to be able to verify Rust code. We want to be able to verify Rust code using a weakest precondition approach and have it handled by automated stat solvers. We want to avoid the challenges that we may face when trying to verify C code, which are going to turn around verifying pointers and require us to use a bunch of really expensive and complex techniques like separation logic or especially memory models. And so the idea here is that we actually want to translate Rust programs into a functional language. And the reason for doing that is that the problem of verifying functional programs has been very well studied, and they're generally much simpler languages than imperative languages. And so it's also usually much easier to verify them. And there's tons of tools, notably Y3, which is a tool to verify, which is a verification tool based around a functional language known as YML. So the idea here is going to be to see if we can encode Rust programs into a functional language, and then just sort of delegate verification to that translated program. And it is possible in the case of Rust programs. And so this approach was first developed by Yusuke Matsushita, Takeshi Tsukada, and Naoki Kobayashi in a 2020 paper known as Rusthorn, which came up with this really, really clever idea, which was sort of to use non-determinism to sort of sidestep the problem of pointers. So non-determinism is a very powerful tool in verification and in sort of formal areas, where we can effectively choose a value. We can make a choice during our reasoning fairly arbitrarily. And so the idea here is that we're going to translate our Rust program into a functional language that has non-determinism. So it has the ability to it has this operator called any, which allows us to pick a value of some specific type. And the idea is that we're going to translate our mutable borrows, so our mutable pointers, into a pair of values in our functional program. And so the idea will be that we're going to translate a mutable borrow into a pair of its current value and non-deterministically guess the final value our mutable pointer has. So the intuition behind this translation is that say we have some value A, and we borrow it for some lifetime alpha into a borrow B. For the duration of alpha, all the permissions of A have been passed to B. We can't access A. Nobody else can access A except for B. No, it really does mean to be divine. Sorry. So for the duration of alpha, the only person who can actually access the contents of A is B, who holds exclusively those permissions. So at the moment that alpha ends, A is going to see those permissions recovered. But what's all the more interesting is that the value A has at that exact moment right here is going to be whatever the final value that B was pointing to was, right? Because B is just a pointer to whatever the contents of A is. And so if we could somehow guess whatever that final value is and just place it in A ahead of time, well, A could sort of pretend to have seen everything that B did. And so that's exactly the idea of this translation. So here on the left-hand side, I have a fragment of some Rust code. On the right-hand side, I have the functional translation of this Rust code. So when we actually create our borrow B from A, we're going to non-deterministically guess the final value of B. And so right here, we're making an arbitrary choice, right? We're saying, I'm going to guess, we're making a choice, and we're actually saying, I'm going to guess the correct value for the final value of B. But that's a fairly complex thing to prove that we can actually make that choice. But we're picking a final value for B. And what we're immediately doing is we immediately reassign A to be whatever the final value of B is. And again, the intuition for this is that previous slide where the moment that we recover A, well, whatever value we recover it with must be whatever the final value B had at the end of its lifetime. And so the idea here is, well, we can just preempt it. We can just immediately, at the moment we create B, we can just immediately assign whatever its final value is to A. And then whenever we start using A again, whenever the lifetime of B is done, well, we already know whatever value is there. We guessed it. We made this non-deterministic choice. We guessed the correct value. So we don't need to bother ourselves with reasoning about memory and heaps and all sorts of things. We can just sort of guess the value that we wanted anyways. And so as we execute our Rust program, in our translation, we sort of follow step by step. So for example, if we try to write 5 into B, well, all we do is we update in our translation, we update the current value of B, right? So now we say, okay, well, now the current value of B is 5. But then we have one additional thing, which is whenever B is done. So whenever we drop B in Rust parlance, which is something that is automatically done by the compiler. In our translation, we add this other statement, which is we add what's called an assume. And assume is another special instruction related to non-determinism, which basically, which allows us to place a constraint on a previous non-deterministic choice. So when we hit this assume, we force the choice that we made up here on line 1, this any, we force it to be whatever the current value of B is right here. And so by doing this, we've sort of magically updated A to be whatever the correct value is. And all of this is without actually using any references or any pointers or anything like this in our functional language. We're just picking a random value and it just happens to be the correct one. We're forcing it to be the correct one, actually. And so using this, we can easily show that A is going to be 5 at the end of our program. Since A is just the final value of B, and the final value of B is its current value, and the current value is 5. So this approach, which was first developed by the authors of Rusthorn, though they applied it to a different translation, is incredibly powerful because it allows us to use mutable pointers without actually having to really reason about any of the things that pointers usually force us to reason about. We can really talk about them in a much more abstract and high-level way, and especially in a way that automated provers really, really love. And, oh, I forgot I had this slide. Oh, well. So when we take the previous little incrementing example that we had in Rust, we can translate it to our functional language here. And so this is what it would give. So our little program, which just incremented the value pointed to by A with whatever the value pointed to by B is, just becomes this. So here, what we do is we update the current value of A with whatever the current with whatever its current value is plus the current value of B is. So it's just doing a normal plus equals kind of thing. And as I said, whenever our borrows go out of scope, whenever they die, we place assumptions here. We constrain the non-deterministic choices that every borrow must contain. And by doing this, we actually force our previous non-deterministic choices to have been correct or to have satisfied a specific condition. So, as I mentioned before, safety is really the most basic property we generally want to verify. In the case of Rust programs, this means especially that this basically corresponds to panic freedom. And the way we phrase this property is going to be saying that Well, given some well-typed Rust program, if our translation is safe, so it is safe in the translated language, which means if our functional program doesn't crash, well, then our original program also doesn't crash. And so we did this proof on paper. It's rather challenging. The actual proof takes like 20 pages to write out, and it's full of tedious cases. The real challenge here is showing that we actually can make those non-deterministic choices, showing that there actually is a choice that we're allowed to make. And so that's the whole difficulty of this proof. And so we're actually working with the authors of Rusthorn and the Max Planck Institute for Software Systems to develop a new proof based off of Koch, which will allow us to have a lot more confidence in the results. And just generally also prove a slightly more powerful and flexible version of this theorem. But then, as I mentioned previously, safety is only really the most basic property we want to verify. We typically also want to verify functional properties. So they're going to be input and output properties on our program. We want to say, hey, this function actually sorts a list, or hey, this function zeroes out a linked list, something like that. And so for that, we need to first say, how are we going to actually describe our specifications? What formalism can we actually use to write down what it means for a Rust program to be sorting a list? And so this is a project that I'm actively working on. And so what I've been developing is a non-executable program logic. This means that your specifications exist purely at compile/proof time. They don't actually get checked at runtime, unlike things like the assert macro that you may have in Rust, which will actually run code that will panic if whatever assertion is not true. There is a very important reason that we are looking at non-executable specifications. It's because that they're strictly more powerful than executable specifications. The work I've been doing has been placed it can be placed in the tradition of other behavioral specification languages like ACSL, which is the specification language behind the Frama C verification toolkit, JML, the Java, I actually don't know what the acronym means, Java markup language, which is the Java specification language, and Gospel, which is a specification language for OCaml. Designing a specification language often requires us to add specific constructs related to the language that we're dealing with. So for example, in ACSL, you have to have operators in your specification language that are going to deal with pointers because they're going to appear in your C programs and you want to talk about their behavior. And in the Java one, they have tons of complex things that talk about classes and behaviors of subclasses and things like that. Well, in Rust, we definitely want to talk about borrows. We want to talk about our mutable references, our safe pointers. The question is, what do we want to say about them and how do we want to say it? And so another Rust verification project called Prusty has developed a notion of pledges, which the idea is you pledge that a property is going to hold whenever your borrow is done. and so this is incredibly natural when you look at sort of the formalism of how we verify Rust, but it also makes a lot of sense even for, I think, for developers, in the sense that there is this very pervasive notion of lifetimes in Rust, and so it's very reasonable to talk about, well, the end of a borrow, the end of a pointer. And you want to be able to talk about properties that are only restored sort of at the end, whenever that pointer is released. But the approach that we're looking at is very closely related to pledges, but it's sort of a different syntax and a little bit more flexible syntax. And it's something we call prophetic values. And it's also been implemented in other languages at this point, notably Spark, which is the sort of provable fragment of the Ada language, which has recently added pointers and has a notion as well of prophetic values in specifications. So let's take a look at what a specification is. What a specification is in the case of Rust. At its most basic level, our specifications are composed of two portions. We have our logical terms, and we have our predicates. So terms are sort of a fragment. It's a fragment of Rust that is happening at the specification level. So we have things like pairs. We have things like dereferencing. We have constants, things like that. These are really sort of terms, expressions of our specification. And then we also have predicates. And so predicates are sort of the real logic side of things. So in predicates, we'll have things like logical conjunction and disjunction. We'll have logical implication. We'll also add quantifiers. So we have for all and exists. So we can actually start talking about for all inputs, property P holds, that kind of stuff. We also have logical equality, which is sort of a more powerful form of equality compared to the standard program equality. But as I said before, we want to reason specifically about borrows in the case of Rust. And so we add two new operators into our terms, which we call @fin and @now. And we'll take a look at what those actually mean in just a second by looking at an actual specification. So here's a specification for the little tiny example we had earlier on. And so we want to talk about what incrementing a function actually means. And so in our case here, it means two things. It means that after we evaluate the increment function, whatever value pointed to by the value pointed to by A has now been incremented by whatever was contained in B. But it also means, but we also have something additional to say, which is that B hasn't been changed. Because B here is also a mutable pointer. We could have secretly modified B. We could have stored 0 inside of it. We could have flipped A and B, done some crazy stuff. So that's also something that we want to ensure about our program. And so that's what we write up here in these two clauses here, where we're specifying behaviors of our program. And so what we say here is that the final value of A is going to be equal to whatever the current value of A is at the entry of our function, plus the current value of B at the entry of the function. And we're also saying, well, the final value of B is whatever the current value of B was at the moment we entered our function. And so through this fairly concise specification, we can actually start talking about the relation between a pointer at some point in its lifetime and its value at the end of its lifetime. So and so so these operators at fin and at now can only be used on values of mutable pointer type, of mutable reference type. So values of some type and mute. And the value of an at fin refers to the value of a borrow whenever it's dropped, effectively the value at the end of its lifetime. Whereas the value at now refers to whatever whatever value that pointer has at its current position in the program. But maybe a point that may be a little bit abstract here, which is in our specifications, we don't actually know the value of at fin when we're proving things. We just know a sort of symbolic value for it. We're refining information, we're placing relations and constraints on at fin. When we prove this previous example here, we don't actually know what the final value of A is. We just know that whatever it is must be the current and values of A and B. We don't actually have a numerical value that we can use in our proofs. We just have symbolic values. So to answer the question of Vitor, I hope I'm pronouncing your name correctly.
Yeah, could you read the question?
Yeah.
Sorry.
Yeah, you're right. The question was, those were not pre and post conditions, right? Are these inferred? No, these are post conditions here. So on this previous example, these are post conditions that we could add to our program if we wanted to actually verify some sort of functional property. If you don't add any conditions, the only thing you get back out of verification with Creusot is that your program is safe, that your program won't crash, or it'll tell you that your program will crash under some execution, or it will also tell you that it can't prove either case. But yeah, no, this is when we want to start adding actual functional properties to our program, and so we add these post conditions on top of it. Yeah. They could refer to at fin. They're just, I don't think that there's any useful provable precondition where you would talk about at fin. But there is no actual limitation on that. I just don't think you would actually be able to do anything useful. Oh, yeah, and sorry, the follow-up question here was whether or not preconditions would actually be able to refer to the final values of borrows. And the answer to that is yes, of course, you can do that, but I don't think that you'll be able to actually get a useful proof or have a useful property that makes use of that. So we can take a look at what it actually means to prove a program using these post conditions. And so the idea here is we'll actually see how these post conditions play into our proof and how they help us reason about the behavior of our program. So we have our little increment function and a tiny main which calls it. And then on the right-hand side, on the bottom, we have a sort of logical environment. This is like what we know logically, mathematically about our program, and that the hypotheses we're going to have when we're actually trying to prove things. So as we execute our program, we learn additional things. So we learn the value of x and y. When we make our function call, we're actually first performing two borrows. We're first performing the borrows of x and the borrow of y implicitly. So we create those in two temporary variables here called a and b. As I said before, when we translate our Rust programs into a functional language, the moment we create a borrow, we replace the borrow variable with whatever the final value of that borrow is. So now we don't know what the value of x is, we don't know what the value of y is, but we know that they're whatever the value. We know that the final values of a and b respectively. And then we make our function call, and And so we make our function call, and what we get back from our function call is whatever the post condition of our function, whatever the insurance of our function is. And so here what we get is that v1, so a, the final value of a, must be the final value of a, or the current value of a plus the current value of b, so it must be 15. And we also get that v2, the final value of b, must be whatever its current value is. So 5. And using this, it becomes quite easy to see how we can prove this assertion, saying that x is 5. We know that this assertion must pass, right? Or sorry, x is 15, and we know that the second assertion that y is 5 also must pass, since y is v2 and v2 is 5. And so yeah, so this gives us a fairly concise way of talking about our pointers and specifications. It translates quite nicely when we're actually doing our proofs. But we can ask ourselves about whether or not this actually sort of scales up or handles more complex usage of pointers. And so here's an example of a slightly more complex program. The idea here is we have some singly linked list type, right? So this is the most basic linked list that you can get. If you've done any functional programming, you should probably recognize this type. The one key thing is that we fixed the type of elements to just be U32, just because. And we want to write a function which takes a mutable pointer to a linked list and zeroes it out. We want to write 0 into every cell of our list. This example is actually translated from the Ada Spark test suite. So they actually also prove this example as part of their test cases for proving things about pointers. I just thought it was a quite neat example and relatively small. So the actual body of the loop is relatively simple here. We have a while loop, a while let loop in Rust, which is basically a combination of a while loop with a match statement, a case expression. So we're basically saying, well, as long as our loop variable or our loop L, our list, is pointing to a const cell of our list, well, we want to keep deconstructing it. So we take loop L, we look into it, and we say, okay, we have a const. Well, recover a pointer to whatever the value is and a pointer to whatever the next element of our list is. And so then we can write into our value, we can zero it out, and we can just update. We can squash our loop variable to be the next cell of our list. And so this will keep executing until it finds a nil, at which point it will. And so I'm actually going to flip these two slides just because I think it might be a little bit more intuitive. We want to talk about what specifications we actually want this function to satisfy. And so there's sort of two properties we'd like to have. The first one is that we'd like to say that for every element inside of our list, at the end of our function, we're going to have 0. So this is what this first property says. So we say that for every index, which is smaller than the length of our list, when we look up the value inside that, the value at that index in the final value of our list, we're going to get back a 0. And the second property just says that we haven't added or subtracted any elements from our list. So we just say that the length of the final value of our list, this final pointer, must be the length of the current value of the list. So it says that the length of L at the end of our function must be the same as the length of L at the entry of the function. And so we can, these two functions, len and get, we actually define directly in our code as well. So we can write little fragments of Rust code. As I said, our program logic includes in its terms a fragment of Rust is sort of the pure expressions of Rust. And so we can write little fragments of Rust code which help us write specifications. And so we can actually write len here as a recursive function on a list. And so all it does is it just deconstructs a list and adds 1 to its length. And whenever the list is 0, or the list is nil, it returns 0. And then we can also write a getter for our list, which basically just looks up the ith element of our list, the ith element of our list. And in the case that the list is too short, well, we return none. So we get option of the U32 back. These two functions also have this type int. This type int is not a Rust type. At least it doesn't exist in standard Rust. This is sort of a logic specific type. This is the type of mathematical integers. So it's an unbounded integer type. It's an unbounded integer type. But we can treat it, we can use it. Yes, so the Alex had a question which was if this is some kind of ghost code. Yes, it is a kind of ghost code. Ghost code is code that does not exist at runtime, that gets that would get erased during compilation. It's code that only exists in our logic, and we can only use while proving programs. So we can write these little helpers for length and getting, and we can then use them to express our specification in a fairly concise manner. And so here we express the two post conditions of our zeroing function. But to actually verify this, we actually have to do one little further bit of work, which is we actually have to add what's called a loop invariant. So we actually have to state some property that is going to be preserved by our loop, which we can then use to actually prove whatever post condition we want to prove. And in this case, this blob of code is the loop invariant that we want. It has a rather interesting property. You may notice that the two lines here, for example, look quite similar. And that's on purpose. Down here as well, that there's a very similar repeated part. In fact, the only thing that changes is the name of the variable that we're talking about. This is based off of a very interesting remark in a paper about the power of loop invariance, but it's really specific to these linked lists and these kinds of examples. If people are interested in this, I'm happy to discuss it more, but it's sort of a gimmick that helps make this proof go well. But equipped with these loop invariants, we can actually generate the code for, we can actually generate the functional code for this Rust program, throw it at our solvers, and they'll tell us that our Rust program actually satisfies its specification. And so we have plenty of work that remains to be done. I'm only in the first year of my PhD thesis, so there's still plenty of time for me to continue working on this. In particular, as I said earlier, we're working on a new proof of this kind of translation with the authors of Rusthorn. And so we're currently undergoing the work of actually doing that proof. there's also plenty of work to do on our program logic, which in particular extending it to all the sort of standard features that we expect in program logic from for other languages. Notably things like labels, things like ghost code, and things like ghost fields, which I didn't get to discuss, but are more advanced features that are quite useful when you're trying to verify complex programs. And then most importantly, it's adding support for a larger fragment of Rust. So what I didn't explicitly discuss here is that we can handle a core fragment of Rust. So that means, you know, Rust expressions with arithmetic, function calls, matching, all that kind of stuff. It's a fairly complete fragment, but and mutable borrows and immutable borrows, but we actually can't handle some other pretty important Rust aspects of Rust, notably traits, which are used everywhere in Rust. So it's like type classes in Haskell. We can't handle closures as well, which are fairly frequent in Rust, though not as common as in functional languages. And we can't handle this kind of nifty and important feature in Rust called interior mutability, which allows you to sort of cheat the borrow checker, cheat the type system of Rust. But it's a quite important pattern for the specific use cases where it's employed. And so those are future directions for work, and we have some ideas on how we can actually attack those different problems. And so, yeah, those are probably going to be some of the most interesting things that we get to work on in the coming years. Yeah, that's everything I had to say.
So before you start jumping into questions, I do want to give people a chance to unmute and ask their questions in their own voices. It gives the illusion of a group experience somehow.
I just want to say thank you to everyone for listening to me ramble like this for I don't know how long. I hope it was clear. If you have any questions or if there's anything unclear about what I said, don't hesitate to let me know.
Yeah, and I just wanted to say also thank you so much for a fascinating talk. I mean, I think this kind of material is not always easy to present, and I can't claim expertise personally, but I got something out of listening to it. I'm gonna have to watch it again, of course.
Yeah.
But first of all, I want to give people a chance to ask some questions in chat. We have a few already, and I'm gonna do my usual stalling technique of asking a less clever question, which is how you got into this, especially since you started out as a site reliability engineer. And did that actually like lead to a natural segue into formal verification? How did you end up doing a PhD?
I mean, I think it all originally started when I took a compilers course back in undergrad. First of all, it was my first real experience with languages, and I realized they were super fascinating. I also made the really poor choice of implementing the compiler alone. I did the whole group project alone, and I decided to use Haskell for it when I had never used Haskell before. But it turns out it really made me discover functional programming, and I got really interested in these kinds of questions of verification as a result. And then working as an SRE, like a huge part of SRE work is going to be, you know, minimizing error rates and ensuring that your software is reliable, right? Which has a sort of natural tie-in to verification, where if you could just prove that certain kinds of bugs didn't exist in your software, then, you know, that's just that many more crashes that you can avoid. But eventually I realized that I actually preferred, you know, going to school rather than actually working. And so I made the jump back into academia to do a PhD.
You gave up a salary for education. That's admirable. I was in a PhD program until I was in a PhD program for a long time and then teaching for a long time. And I finally got into industry when I was 37 or 38, something like that. So I went the other direction. And I hope it works out for you.
Yeah, I hope so as well.
Okay, so questions are rolling into chat, starting with Vitor. I'm going to expect all of Xavier's friends who are here tonight to ask a nice question as well. Support your friend with a thoughtful and intelligent question, please. But Vitor, would you like to unmute and ask your question?
Hey, sure. Thanks for a great presentation. So, what was my question? All right. So we were using len to the post condition of yeah. So here len is defined as a recursive function, and I was wondering if that's important, or like couldn't we have written it as a while let as in the other case?
So in our logic, at the very least for the moment, yes, you have to use a recursive function. What's important to keep in mind is that I do believe that it could be possible to relax this restriction and allow while loops here. But what's important to keep in mind here is that in our logic, we have to be pure, which means that we have to avoid mutation. So we can't allow you to mutate values in the logic, because that doesn't really make sense. So just imposing that we have recursive calls, it made it easier to check syntactically that we were pure. So you're only allowed to do things like deconstruct values, arithmetic on values, and read references and make function calls based off of that. You for example can't do an assignment, or you can't mutate a borrow in the logic. Yeah. So yeah, for the moment, you are required to do a recursive version of length rather than an iterative version.
Okay, so next we have a question from Alex. There are multiple Alexes in the chat. So this is like Alex without a last name.
Can you hear me?
Yeah.
Seems so. Okay. Yeah, sorry about the last name. I forgot. Yeah, my question is, thank you very much for the talk first. It was interesting. My question is so we can only define properties where the function is defined, right? So we cannot have an extra pool of, I don't know, an extra module where we can extend additional properties. So if I would like to write some, or verify some properties of your library, I would have to patch your library actually.
So so I think that there's two parts maybe to this question. So the first thing is, of course, is sort of how we handle external code, or it's really, it's how we handle external code. So the immediate answer is we don't at all. You cannot use external, you cannot have any properties on functions from external crates. That's purely an implementation restriction. It's just I haven't had the time to implement the code that would allow you to do that. The second thing is I don't think you'll ever be able to prove properties about code from external crates. You would have to actually go into that crate's code and prove the property there. Like you wouldn't be able from your project to prove that some function in a different crate has a specific property. What you could do, and what I'm planning on adding, is allowing you the ability to assume that external functions satisfy a specific specification. So for example, you could assume that the standard library vector satisfies some specification, you know, for example, that like binary search behaves properly and returns an element that matches your condition or whatever. And so that is something I'm planning on adding, the ability for you to say that external code satisfies some pre and post conditions. Yeah. Did that answer your question?
Yes, thanks.
Okay, and then we have another question from a different Alex. So
right.
other Alex, would you like to unmute?
Yep, right. Hello, yeah, and thanks for the talk. I'm not really into like verification of Rust programs much, but I've heard there's a few efforts like Rust Belt, Oxide, stacked boroughs models. Like, do you know how they compare to yours?
Yeah. So so Rust Belt and Oxide are both attempts to formalize the Rust type system in particular. Oxide has gone under some pretty big revisions recently, so I'm not too familiar with how it like the details of how it works now. But I am more familiar with how Rust Belt works because the proof that we're working on right now is actually based as an extension of Rust Belt. And so Rust Belt actually basically embeds the Rust type system into a framework known as Iris, and essentially allows you to prove it proves several properties about the Rust type system as like a mathematical lemma, notably that if a program is well typed, it's going to be memory safe and data race free. So that's really, really cool. But you can't actually verify functional correctness in Rust Belt, though in a way the proof that we're doing would change that. And stacked boroughs is more of an attempt to give unsafe code proper semantics, if I understand it correctly, which is more about defining what you're allowed to do in unsafe code. And what you're not allowed to do, and what are the specific reasoning rules around that. And so I'd say that it's sort of orthogonal to the work I'm doing anyways, because we're only looking at safe Rust. But working with stacked boroughs would be a prerequisite for sort of any tool that tried to verify unsafe Rust. Because it sort of defines what's allowed. Did that answer your question?
Yeah, thank you.
Bernd wants to know if there's a live demo.
Yeah, I mean, I can definitely do a live demo. I believe I just need to change what window. I'm just going to share my whole screen. So as Creusot is still very alpha quality software, we don't actually have a fancy UI for it yet. We sort of just generate code and then we dump it into Y3. And then Y3 has an IDE that we can use to actually prove code. Future versions, I would very much like to have something like a VS Code plugin, which allows you to see your Rust code and directly on your Rust code, like see proof information embedded in it, like, you know, oh, at this line of your Rust code, you have some proof obligation that you need to prove. But for the moment, that's not the case. So you'll just have to bear with me on that, sadly. So as I said, we have take a look at a different function than the one I showed during our test, during the presentation, which is indexing a linked list, mutably indexing a linked list, which is sort of like, which is a weird usage of linked lists. But if we imagine that our linked lists are actually arrays, then that's sort of the core operation we want. We want to be able to access some element of our list, and we want to know that we access the correct element. So I'm actually going to just open this in an editor that has syntax highlighting so that we can actually see what it looks like. Do you see this, or did it send it to the wrong place? I believe it may have sent it to the wrong place.
Yes, we can see it.
Okay. Yeah, we can see.
Yeah, okay. So we have our linked list, we have our file here where we define a linked list type. We define the length and get functions logically. And then we define the all too critical index mute function. So it takes as a parameter a mutable pointer to a list. It takes an index and it returns a mutable pointer to, or mutable reference in Rust speak, to some element of our list. We have four post conditions here. The first thing we have is that whatever the current value of the results is, it's the same thing as the ix element of the current value of our list. And we have the same thing for the final value of our list, the final value of the result. So we're basically saying, well, our result is whatever that element of our list is. We also have, again, we have this post condition that shows that we didn't change the length of our list. And then we have another condition, which is quite interesting, which says, for all the indexes that are in our list, that are smaller than the length of our list, that are different from the one that we're looking up, the current value is the same thing as the final value, which basically means that we're not touching those elements. So through this, we're saying that you're going to get back a pointer to one element of our list, but you also know that nothing else has been changed, that the list hasn't shrunk and it hasn't grown. Unlike the all zero example that I showed earlier, we actually also have a precondition here. This is this very first line, which requires that the parameter we're giving is smaller than the length of our list. So it means we're requiring that we're giving a valid parameter. And then we have our loop invariants here, which these loop invariants are fairly, they're a little bit special. Basically, the first one just says that as we go through our while loop here, our index is still valid. And the second one here says that the second and third ones here basically says that as we go through the while loop, if we look into the remaining portion of our list, we get something that corresponds correctly with the original list. And then we have these final two invariants, which are used to prove the final two properties, each respectively, and essentially do the same thing. What we do here is we say, hey, if you look into, if I know that this is true for the current list, then I know it must also have been true for the original list. We're relating, we have this this implication, which is quite a powerful tool, which sort of allows us to reconstruct just one step of the final property that we want to ensure. And this is a trick that's used quite often in verification tools that involve separation logic. It has deep ties to something called the magic wand. So we can just throw Creusot at this. Yeah, if you were to write index mute as a loop invariant would disappear. Yeah, so Vitor asked if we wrote index mute as a recursive function, would we not have to write the loop invariant? We wouldn't, because the preconditions and postconditions would basically act as a loop invariant. And that observation is actually exactly the reason for this sort of weird, these last two, the shape of these last two invariants with this implication. It's actually replicating exactly that behavior. But it's sort of a technical detail of the proof. So we can run Kojo on this, and it's gonna, if we just run it like this. Oh right, I need to actually, I must have. Yeah, okay, I had a bad directory. If we run it like this, it's gonna generate a bunch of code. And so this is YML code, essentially. So it generates a bunch of code. So we can just dump it into an MLCFG file, and we can load it up. We can load it up in the Y3 GTK IDE. and Y3 has remembered all the previous code, but all the previous proofs I didn't, but I'm just going to go ahead and clear them. And so we can go through. And so, as I said, there is no fancy UI that actually shows things on Rust code, but this would be something that we could build on top of Y3. And it's actually meant for that specific purpose. But in Y3, we have this list of tasks, which are sort of different proof obligations we need to accomplish. And we can go through and we can launch automated solvers by hitting the 0 key. And we can see the little question mark turn green. And that means that we've proved things. And so then we can get to more complex examples. If we try to do 0, oh, it actually managed to prove it. Yeah, solvers are incredibly powerful. We can see that it proved it in 295,000 steps. But we can actually also go through, and if this proof had a challenge, we can actually go ahead and ask Y3 to break up the proof that we're doing by hitting the S key. And it very nicely will chop up the proof obligation we have into a bunch of separate proofs that we can ask Y3 to then work on. And so we can see that for each one of our loop invariants in our Rust code, we get 2 proof obligations. We get an initialization condition and a preservation condition. And this is basically saying, well, when you enter your loop, we need to show that this property holds. And then at each iteration of your loop, you need to show that it still holds. That's what makes it invariant. We also get one proof condition for every post condition of our function. We need to show that they're true at the end of our function. We get a couple extra things for unreachable points. These correspond to panics. Basically, if we have something like std abort, we need to show that we actually can never get there, because that's not safe behavior, and we need to show that we're safe. We also get things related to integer arithmetic. So every time we do arithmetic, we need to show that it's correct. So for example, here ix is an unsigned int, so we need to show that we never go below 0, right? But we can see that pretty trivially because we have this loop condition right here. So Y3 will hopefully break these things up, and we'll even actually usually be able to give pretty decent names to each of our proof conditions. And we can go ahead and throw automated solvers at each one of these obligations. Though it seems like it's having a harder time proving some of these independently than it was proving the entire thing. And this is sort of the woes of automated proving, is that sometimes the provers can prove a complicated thing and can't prove a simple thing, and sometimes they can prove a simple thing and not a complicated thing. In this case, I already know what the problem is, but it's just a question of asking the provers to do a little bit of simplification ahead of time, and then they'll be able to go through everything.
I feel like the fact that you're doing this in Rust and that there are already some tools for automating this means it's not impossible to imagine this could find its way into industrial applications sometime, this century.
So 2 tools I mentioned vaguely during my presentation, FramSC and Spark, are tools to verify C and ADA code respectively, and are actually applied industrially already. The big challenge here is that, especially FramSC, which is a C verification tool, they have a hard time dealing with pointers, basically. Like they've done a lot of incredible work there, but they're fundamentally just kind of limited by the fact that C pointers are kind of crazy and can do anything. And so they have to do a lot of complex work to work around that. And we don't have to do that at all. And so we get this nice translation to a functional language, which is so easy to automate, as you can see here. And so, yeah, I mean, I don't think it'll be anywhere near usable by the end of my thesis in an industrial context, but hopefully sometime afterwards.
Someday. So yeah, I agree with you. Don't program with pointers.
Yeah, unless it's Rust.
Yeah, unless you have a borrow checker or something. All right. Bernd, thanks so much for asking about the demo. That was amazing and unexpected, and I think super valuable to see. There are a few more questions, and I think we should probably wrap it up. And I think these are maybe quick questions. First from Hisham. Hisham, do you want to ask your question? I know it's a very small one, but I'm trying to get as many voices as possible involved.
Hey, sure. Yes. Hi, Xavier. Thanks for the talk. I think we bumped into each other at LuaConf a couple of years ago. So
oh,
nice
wow. Yeah. Yeah. Wow. Crazy.
Yeah. So it's well, I was doing my PhD, so it's cool to see you doing your own research and doing some cool work. So yeah, my question was related to something you just mentioned about pharmacy. And so is the unsafe fragment of Rust essentially equivalent to C?
No, it is not, because something that was mentioned previously called stacked borrows, which is sort of the semantics for unsafe Rust code, which are significantly more restrictive than what you would be allowed to do in C. So you're not you're already not allowed to have like all the craziness that you would in C, though you have a lot more than what you're allowed to do in safe Rust. But also in unsafe Rust code, a key part of Rust is this idea that we can abstract over unsafeness, right? So unsafe code has to be in a block, and there's this contract that right now isn't really checked by the compiler, but that you're supposed to hold up, which is when you exit your unsafe code, you've restored all the properties that the Rust type system is assuming, right? Which means things like mutable references aren't aliasing, they all point to valid memory, all these things. So it's not really the same as C, but when you're in unsafe code, you get access to things like raw machine pointers and a lot more power. But you have more responsibility writing that code than you would in C. Yeah.
And it looks like we have one more. I'm sorry, Hisham, did you have a follow-up?
No, just thanking.
Okay, thank you. I think Vitor has one more question.
Yeah.
Oh yeah. So there's this tool called Stainless, which I think was originally built for Scala code, but now there's a Rust front end, and I think it looks I don't know much about it, but it looks similar to what we saw here today. I was just wondering if you came across it, and if so, if you know if there's any common points or anything like that.
I haven't actually heard of this tool before, so I really can't say what we have in common. The main big Rust verification project that I know about and follow is Prusty, which is based on a verification platform called Viper. But I've never heard of Stainless, so I'll have to take a look into that.
Okay, no more questions, but actually we got a lot of good questions. And this is one thing I kind of pride myself on for this meetup. We always get lots of interesting questions for the speakers. So I hope that was interesting and fun for you, Xavier. It was really great to have you.
Yeah, I just really hope I didn't make too many mistakes and that I didn't confuse people more than I explained.
Oh, who cares? You were great. So you're are you in Paris now?
Yeah.
Okay. Yeah. So you're my lockdown buddy.
Yeah.
Although,
super lockdown.
I think things are a bit worse in Paris than they are even in Berlin, and they're pretty bad here.
Yeah, we don't get to go outside after 7.
Well, on behalf of the meetup, I want to wish you the best of luck in your studies, and I hope that someday when things are different, you can visit us in person and do a follow-up.
I hope so too. Thank you so much for inviting me, and thank you everybody for coming.
Yeah. Thanks so much to the audience for listening and for your great questions. And you can see this talk on YouTube very soon. Bye-bye.
Bye.